Hello and welcome to 7.2 where we're going to be looking into exponentials. So this is one of the most useful functions we kind of learn because exponentials is used in all kinds of disciplines like economics, biology, population growth / decay, all kinds of things like that, finance. So here we go. Let's look into it. All right, here we go. So first of all, what are these exponential functions that we're talking about? And they just look like this. So it's just a fancy word for saying we have a number and some stuff in the exponent. So we'll notice here that our variable is now in the exponent. And so this is important to know how to use this stuff, like I was talking about in the intro, in things like economics, biology, population growth, decays, things like that. This function, being able to change this variable, is very useful to be able to predict profits, predict population growth, things like that. So let's learn how to use it. When we have a situation like this, we're just going to use the properties of exponents to simplify each side of the equation. Most of them are, so that one is simplified. Here we would simplify that one, things like that. Rewrite the equations so that they have the same base. Remember, the base is the big number. So as long as we have the same base, we're good to go. Some of the problems like this one down here don't have the same base. So, we'll cross that bridge when we get there. And then you drop the bases and set the exponents equal to each other. So in my mind, that kind of makes sense. So if we have 2 raised to the power of x plus 1 equals 2 to the 9, it makes sense that we could just go x plus 1 equals 9, right? I don't know. It makes sense in my brain, but those are the methods that we're going to use. So if we were to do number 1, we see that we have 2 of the same bases. So we're just going to set x plus 1 equal to 9. We're going to subtract 1 from both sides, and then our x equals 8. And that's it. Our answer is x equals 8. So same thing for over on number 2. We've got 5 raised to whatever equals 5 raised to whatever. So we're going to drop the bases, and we're going to say 4n plus 5 equals n minus 7. And then from there, you're going to put all of your variables to one side, all your numbers to the other, and then solve just kind of like normal. So we're going to move the n over to the left. That's supposed to be an n. So now we have 3n. We're going to move the 5 over to the right. 7, 8, 9, 10, 11, 12. I knew that. Equals negative 12. We're going to divide both sides by 3. And then we have n equals negative 4. So for this part, it's that easy. Well, as soon as I say it's that easy, things get more complicated, right? So now we've got this thing here, which that gets weird. We can't just set all of these things equal to that. But remember, we've got some properties of exponents, right? So these are the same base still. And when we're multiplying the same base with the exponents, that just means that we're going to have 3 raised to the power of k, that's that one, plus k plus 2, which we can then simplify that as 3 to the power of 2k plus 2. Oops. Plus 2. So then now we can set that equal to our 3 raised to the power of 5k minus 1. And then we're going to go back to what this section is all about. And we can say 2k plus 2 equals 5k minus 1. And then from there, we're going to solve. So I'm going to bring all the letters to the left. Minus 5k. Bring all the numbers to the right. Minus 2. So now we have we have negative 3. So we have negative 3k, because 2 minus 5 is negative 3, equals negative 3. So then we divide both sides by 3. We get k equals 1. And this is supposed to be a k. Okay, what if they don't have the same base? Well, at this point, we're just going to essentially be clever to get them to the same base. So we're going to look at this. We've got a variable in there. So this base is not changing, right? That seems like it's going to be hard to do. But this number, what do we know about 36? So we could rewrite 36 as 6 squared. And then at that point, we would then have the same base, which would allow us to do the property that we just learned. So we're going to rewrite that 36 as 6 squared, and then we can set them equal to each other. And that means that we would have 2x minus 10 equals 2, because 36 is the same as 6 squared. So then we do some algebra, plus 10 to both sides. Then we're going to have 2x equals 12. We're going to divide 2 to both sides. We're going to have x equals 6. So again, we just have to kind of be clever to rewrite the right side so it has the same base as the left. And this is the part that can get kind of complicated. So I say it can get kind of complicated because it really involves you knowing all of those exponent properties that we learned last chapter, and to be really fluid with them. So, for example, with number 7 here, we've got this fraction, but I see that it's 7 down here, 7 down here, so I'm immediately thinking, man, it's got to be something to do with those 7s. We do have an exponential property that says that I can rewrite my 1 over 7 to say 7 raised to the negative first power. So when we do that, we can now set both sides equal to each other, and then we're going to have 4x plus 11 equals negative 1, because again, we're setting this exponent equal to that exponent. So then from there, we're just going to solve. So we've got 4x equals negative 12, because we subtracted 11 from both sides, and then divide by 4. So then we're going to have x equals negative 3. So again, the hard part here is this part is remembering this part right here. So if I were to make a recommendation, maybe put those properties on your note card so that you can kind of have a visual cue of like, oh, maybe I could do this, that, or whatever. So number 9 is a great example of a different exponential property. So here we have this 27 raised to a variable, and we have a 3 raised to a variable. Okay, so how are we going to do that? So we're looking at 3, because that's my smallest number. Is there any way that we can rewrite 27 with a base of 3? So the answer to that is yes. We can rewrite. We can say 27 is the same or is equal to 3 raised to the third power. So remember, 3 times 3 is 9, times 3 is 27. So now we're going to just shove that. We're going to put 3 raised to the power of 3 in 427. So now what that's going to look like, notice the parentheses that I write. So we're going to put parenthesis 3 to the third power, close parenthesis, 2x plus 6. So now when I write it like that, it kind of makes it a little bit more obvious what we need to do next. So we do still have a power of a power property that says, in this case, we're going to multiply those two things together. So now our left side of the equation becomes 3 raised to the power, and I'm going to distribute this to both numbers, raised to the power of 6x plus 18. So 3 times 2 is 6. 3 times 6 is, 18. Sorry. I know my multiplication numbers. I swear. Anyway, so now that we're at that point, so our new problem looks like this. And this is where we can do just our normal thing that we're doing in this section. We're going to set this equal to that. So now we have 6x plus 18 equals 2x. I'm going to move my 2x over to the left. So now we're going to have 4x, and I'm going to move my 18 over to the right, equals negative 18. Divide both sides by 4, and then that's going to be 3. Yeah, negative 3. Someday I'll learn my multiplication tables. So I jumped down to number 19 because it's just a little bit more complicated and it shows a lot of different processes that we're going through. So here I am. I'm looking at this problem for the first time. And I know that I need to find some common bases. So I already see a 7 and I see a 7 here. Okay, so that's common. And a 49 is the same as 7 squared, right? So now we're just going to have to start rewriting all of this stuff in base 7. So my left side, we've done this earlier. So my left side is the same as 7 raised to the negative first power. I said earlier that 49 is the same as 7 squared, right? So we're going to replace that with 7 squared. Notice the parentheses, x minus 5. And then we're going to multiply by 7x minus 9. So we're going to do this first so that once we get a single number here, then we can combine these two. So we're using multiple different exponent properties. So when we take this part, we'll do this part in purple. We're going to take 2 times x, 2 times negative 10. So we're going to have 7 raised to the power of 2x minus 10. And then everything else just comes down. Because I'm a math teacher, I like to do one thing at a time. Oops, x minus 9. So now we also have another exponential rule that says because these are multiplied together, we can just add these two. So don't forget about those rules. Just because we've got complicated things in the exponents, you can still maintain those rules. So we're going to add those together, and we will do that in red. So that means that we're going to have 2x minus 10 plus x minus 9. We're going to combine like terms. We have 3x minus 19. So now my new problem is 7 to the negative 1 equals 7 to the 3x minus 19. So we just use our exponential rules to kind of change what this looks like into this. We haven't actually done the solving part of it yet. We're just manipulating the equation so that it looks easier, or it looks better, or better able for us to solve it. So then from here, we're just going to set our exponents equal to each other. So that means we're going to have negative 1 equals 3x minus 19. I'm going to keep that 3x on the right just for fun, which means my 19 is going to come over. So we're going to add 19 to both sides. And then we're going to have, what? Positive 18 equals 3x. We divide both sides by 3. X equals 6. Apparently I need to practice my 6 multiplication table. So those are a couple of examples. You can always look at more examples if you want, but we're obviously going to do some more in class. So I'll see you there.